So, we have all the machinery necessary to establish and formalize the concept of the Fourier expansion of a Boolean function. And what we will need to build is the machinery of multilinear polynomials. So, I will pause just for a minute and go a little more slowly, because till now what we have seen were elementary introductory definitions, but now we are getting into slightly more complicated machinery. So, we all know what polynomials are. A multilinear polynomial is a polynomial that is linear in each of its variables. So, the degree of the multilinear polynomial is the maximum number of variables that occur in it. So, as an example, you have the multilinear polynomial ax1 plus bx2 plus c times x1 x2 plus d. This has a degree 2, and if you notice, x1 and x2 are, whenever they occur, are raised to the power 1. That makes it linear. As a counterpoint, let us look at the polynomial at the bottom of the slide, ax1 square plus bx2 plus cx1 x2 plus d. This is not multilinear for the obvious reason that x1 in the first term of the polynomial is raised to the power 2. Okay? So, a, b, c, d using standard convention are the constants that multiply the variables x1 and x2. So, these are multilinear polynomials, and it turns out that they are not just there since they are interesting mathematical concepts, but they are there because we will use them to construct the Fourier expansion of Boolean functions, which is really what we are trying to do now. So, at a conceptual level, at a high level, the Fourier expansion of a Boolean function is its representation as a real valued multilinear polynomial. So, the x's in the previous example can take on real values, as can the constants. So, that is the most general form. So, if you look at the Boolean function we have been studying as an example, the max2 function, and I will not again repeat since we have just seen it what it does. What can be a multilinear polynomial representation of such a function? It will take us quite a bit more time to find methods for building or deducing such polynomials given Boolean functions, but before we do that, let us just convince ourselves that this in fact, namely rewriting Boolean functions as multilinear polynomials, can be done. So, the multilinear polynomial for max2 we show as if we pulled it out of a hat like a magic trick is half plus half x1 plus half x2 minus half x1 x2. In the table below, we actually make sure we verify this fact, where each row of the table represents a distinct input to the max2 function, and the last column represents the column vector which was the outputs, which we call the vector representation of the max2 function. Straightforward exercise to go through row by row and in fact convince ourselves that the calculations are correct, and the polynomial gives us the output values that are consistent with the definition of max2 for each possible input, and we have 4 inputs. So, just out of a need to gain some experience, we will also from time to time consider another Boolean function which is written Maj to the subscript 3, it is the majority function. So, it takes 3 input bits in this instance because, and hence the number 3, which are strings of length 3 built from symbols -1 and +1, and depending on which symbol occurs the most, the majority, it returns that symbol, namely either -1 or +1. So, it is a single valued output, and that is the result. So, we can sort of suggest an exercise, and it is not difficult, to try, as we did in the previous example for max 2, to guess a multilinear polynomial representation for the majority 3 function, and we just give you as a bonus the answer in this case. So, the verification for that this indeed is the correct representation for the majority function, where the polynomial is half x1 plus half x2 plus half x3 minus half of x1 times x2 times x3, that indeed represents the correct answer, is something you could go through and verify simply the way we did exactly in the case of max 2. But of course, given some strange Boolean function, we need to determine how we can write out a polynomial like this, and that is where our end goal is for this entire exercise, to write out an expansion that gives you a multilinear polynomial representation. So, to do that well, and when I say well, I mean systematically, we need the concept which we will switch to now, and that is called an indicator polynomial. It is a particular type of polynomial that is extremely useful in thinking about writing out Fourier expansion. It turns out that it is an important first step, and I would say a first step out of 2 important steps in taking a Boolean function and rewriting it as a sum of terms that are a multilinear polynomial representation of it. So, what is an indicator polynomial? An indicator polynomial takes an input string at a time. So, you have n possible input bits, so length n, and let us say that you fix a string from this set of 2 to the n strings, a1 through an, that is a fixed string. Then the indicator polynomial, which is syntactically written, and this is directly from the book I referred to earlier, by the number 1 with a subscript a, which is our n bit input that we have picked, and some possible input string to the Boolean function x. So, x is a variable string, can take on any value from the 2 to the n values, a is a fixed string. The indicator polynomial has the important property that when you substitute x into the polynomial, it will return a value of 1 exactly when a matches x. Notice that x can take on any one of 2 to the n input values, of which a is 1. If you change the value of a to some other fixed input and cycle through all the values for x, same thing again. When it matches, it will return a value 1, otherwise it will give you a value 0, and that is called the indicator polynomial, perhaps to pick up on the idea that it is indicative of what the input is. You can think of it as raising a flag saying yes, I matched with the input when x and a are identical, otherwise it gives you a value 0. And an important step in building up the Fourier representation as a multilinear polynomial, and if you recall from the previous slides, we could at least for 2 functions, a max 2 and majority 3, write out such a polynomial. Now, we are headed towards doing this more generally. So, the end goal is to write out the value of the Boolean fx, the Boolean function, as a sum of, for each input, the function value for input a times its indicator polynomial. So, that is the form that we wish to go towards in representation. So, given that that is our goal, let us spend a few minutes trying to think, and it takes maybe 5 to 8 minutes at most, to how to write out these indicator polynomials that have this magical property that they match the input and produce a value 1, and they mismatch the input, they produce a value 0. So, to compute this particular form using indicator polynomials, we will go to our favorite function and try to see, at least intuitively, how we would do that. So, once again, rather than going through a general method which we are headed towards, we assure you, we will take a look at the example of the max2 function, and once again sort of magically work out as if we know what the solution should be, but at least understand structurally what an indicator polynomial ought to look like. So, what we have is basically a form where the things or not values that are not in parentheses with the values x associated with them are the function values, and these were derived, if you recall, we had a vector representation for the max2 function which had +1, +1, +1 and -1 as outputs. For simplicity, we will just ignore the +1 symbol in this slide. So, we will write +1 as simply 1, and of course, -1 as -1. And the indicator polynomial structure itself takes on the form that you see there, where the first term is 1 plus x1 divided by 2 times 1 plus x2 divided by 2, and so on. Intuitively, the inputs for this, if you recall, the 4 inputs were +1 +1, -1 +1, +1 -1 and -1 -1. So, the way the polynomial works is the input bit value is also the sign bit for the particular instance of the variable xi. So, if you take the second term, which has the indicator polynomial structure 1 minus x1 divided by 2 times 1 plus x2 divided by 2, then this was associated with the input -1 and +1. The output value is 1, which is multiplying the whole expression, and then inside we have the values 1 minus x1 by 2 times 1 plus x2 by 2. And if we simplify this, it is a simple enough exercise, if not entirely trivial, to get exactly the form that we had earlier pulled out of our hat for this function max2, and we claimed at the time that this is leading towards our end goal of coming up with a Fourier expansion and representation of this particular Boolean function. So, now a little more generality going beyond this example, let us focus our efforts on trying to construct these types of indicator polynomials for an arbitrary given Boolean function. So, you have input values 1 through n, and for each such index value I of the input, we would want what we call a monomial mi in xi that evaluates to 1 if ai equal to xi, the ith input, otherwise mi equal to 0. So, as a guess we could say, okay, is mi ai times xi? It is a simple counter example to deduce that this does not work for all Boolean functions. So, then we come up with our magical form, mi is actually 1 plus ai xi divided by 2, and it turns out that works. So, when we actually construct the indicator polynomial 1a of x, it is a product of these m1s, m2s through mn, and the reason it works intuitively is this product equal to 0 whenever at least one of its values is 0. So, you really want all of the values to be 1 for the entire indicator polynomial to be 1 or evaluate to a value of 1. And so, continuing, the indicator polynomial itself takes on the form 1 plus a1 x1 divided by 2 times a2 x2 divided by 2 times 1 plus a n x n divided by 2 for each possible input. So, just to remind ourselves, the xi's are drawn from n possible input values from the set plus 1 and minus 1, and returning to the max 2 example, we will see in a minute or so that this indeed is the exact form that we showed you when we pulled this polynomial out of our hat as an indicator polynomial for the max 2 function. So, in the equation that we just saw, we have 4 possible inputs. So, there are 4 distinct indicator polynomials, 1 for each possible input, which will evaluate to 1, and again, not to forget our overall goal, it is really to write down the function f of x as the product of f of a, the particular function value with input a, which is one of the 2 to the n input strings, times its indicator polynomial value I in our notation sub a of x. So, returning to and repeating that example again, now you see that you can write down using this form, since you have 2 input bits, you do not have n input bits. What you have really is the first term is 1 plus a1, which is 1 times x1, times 1 plus a2, which is 1 times x2 divided by 2. Second, the value 1 minus x1, because the value is a1 is minus 1 in this case, the input is minus 1, at times 1 plus x2 divided by 2, and so on, which gives us the particular simplified value. So, more generally, how do we do this for Boolean functions that are arbitrary? So, they do not have to be the max 2 function. So, just as a very simple but a useful exercise, we will consider extending our methods to any Boolean function, where you have given the function f and you know that the form we are seeking is for the first value a1, the indicator polynomial times the function value, through the ith value ai times the indicator polynomial for the ith value, times all the way to the last value, which is ranging over, as you know, inputs 1 through 2 to the n. So, the last value is 2 to the nth value times the indicator polynomial for that particular value. So, that is what we are seeking. Why does this form work is the question we have to ask first before we algebraically simplify and try to deduce it for a given Boolean function. The answer is actually quite simple. So, when you are given the value a1, x equal to a1, only the first indicator polynomial is working, and when f gets that input, it outputs the value f of a1, because the indicator polynomial in the yellow box gives you a value 1. So, it is 1 times f of a1, which is exactly what you want when x equal to a1. The other terms go to 0. Similarly, you get this form, which is f of a1 times aai times the indicator polynomial for the value ai. So, when x equal to ai, this term will be the only non-zero term which matches x again, and so on till the last value. So, how do we take this intuition and then try to write it down in the form that we earlier looked at, which is a product of individual terms, which when multiplied by the function value actually gives us a polynomial of some kind. So, if we go through the calculation and write out the value, it turns out we can actually write this as a sum that is quite long, because you have 2 to the n possible inputs, but the sum would take on the form C0, which all the C's are constants, I will remind you, times C1 times x1, the first value, dot dot Cn times xn, the nth value, and so on. These are variables one at a time, plus Cn plus 1, take 2 values at a time, and so x1, x2, x2, x3 and so on, all the way to taking x1 through xn all together multiplied at one time. So, that is just an algebraic transformation where if you wrote out f of a1 times the indicator polynomial value, one can work this out as an equivalent representation for it. So, now you have this long sum where you have the values of xi, the individual inputs to x, right, which are the elements of x, you can think about it that way, and each of these elements of x are now occurring individually, then in pairs, and then all together at the very end. So, these are essentially all possible subsets of x1 through xn. So, building on that intuition, we will now try to deduce what these various combinations are and transform this sum into an equivalent form, exactly the same sum written using more or less a different notation. So, continuing with our new form for Boolean functions, we notice that the total number of terms in this form, the way we have written it, we have 2 to the n terms, and each of these terms are themselves Boolean functions, because if you take for example the term that has a product of x1, x2, since x1 and x2 are Boolean variables, that product is a Boolean function. So, that is a useful thing for us to think about as we move forward, and these are, since they are all no more than powers of one of the Boolean variables, they are monomials. That is consistent with the definition of what a monomial is, and now we will move forward towards using this form in achieving what our goal is, to write any Boolean function as combinations of these monomials. And finally, and this is very important, our end goal is not just to write Boolean functions as monomials, but in fact show that we can construct a basis for the vector space of all Boolean functions using this form. So, that is where we are really headed with this. So, once we have the vector space and its basis, we know that if the Boolean functions form a vector space and we have its basis, then of course, we can immediately conclude that we can represent any vector Boolean function from this vector space through that basis, since that is the very definition of a basis.